Introductory quantum mechanics often treats the electron using a simplified model. Its orbital motion through space and its intrinsic spin are viewed as separate, unconnected properties. While useful for calculations, this assumption is an incomplete approximation that fails to describe the actual behavior of matter. At a relativistic level, these properties depend entirely on engineering these quantum states at the atomic level. This operator links spin to orbital motion, creating the complex electronic states required for these advanced technologies to function. To understand why this coupling occurs, we must start with the relativistic Dirac equation. This is the fundamental origin point for the interaction. High-precision theory uses a low-velocity expansion to reduce that complex equation into the Pauli and bright-Pauli Hamiltonians shown here. From the electron's perspective, the positively charged nucleus orbits around it. This relative motion generates an internal magnetic field interacting with the electron's intrinsic spin. This operator's core is the L.S term, showing energy depends on vector alignment. Note the red 1 on the left, the Thomas precession correction, a relativistic factor preventing the model from overestimating the magnetic field. With this term added to the Hamiltonian, the energy of the atomic system is governed by its internal relativistic geometry. In a non-relativistic system, orbital angular momentum L and spin S are separately conserved, represented here by these two independent blocks. Once coupling is present, that independence vanishes. The atom trades those individual properties to conserve a single fused total angular momentum, labeled J. We observe this fusion in atomic spectra. A single energy level from the gross structure splits into multiple distinct lines. States with the same principal quantum number are no longer equivalent. Instead, they shift and split based on their specific J value. This formula calculates the exact spacing of those levels. The energy of each state is now a direct function of the total angular momentum. This derivation leads to the Landé interval rule, showing the electronic spectrum is permanently reorganized into multiple J-resolved levels. Spin-orbit coupling does more than shift energies. It redefines the good quantum numbers used to describe the state of the atom. The strength of this effect scales dramatically with atomic size. As the atomic number grows, standard coupling rules degrade. In light atoms, electrostatic forces are the primary driver, but in heavy atoms, the spin-orbit interaction dominates, creating entirely different coupling structures. The physical environment changes even further and becomes much more complicated when an individual atom becomes embedded within a dense, complex molecular lattice. In these environments, the clean spherical symmetry of the atom is lost. The asymmetrical fields of the molecule quench the orbital angular momentum, making the simple atomic picture less accurate. This leads to state admixture. Spin-orbit coupling prevents us from mathematically separating the spin and spatial components of a state. As seen under the reality, a normally pure singlet state gains a fractional addition of triplet character. The states are no longer pure. This mixing of states provides the transition intensity needed for physical processes that would otherwise be strictly forbidden. In intersystem crossing, an electron moves between the singlet and triplet manifolds, a transition normally forbidden by quantum rules. When the electron eventually drops from that triplet state back to the ground state, it emits a photon, a process known as phosphorescence. Scientists exploit this by using heavy metals like iridium and platinum to intentionally increase the rate of state mixing. By amplifying the coupling, they can turn a weak, slow emission into a strong, commercially viable light source. This isn't just about heavy atoms. El-Sayed's rule shows that changing the orbital character, such as moving between n and pi star orbitals, can also enhance the effectiveness of the coupling. Whether through heavy metal complexes or precise orbital design, engineers use this operator to tune the colors and lifetimes of modern displays. Modern dynamics reveal a deeper layer of complexity. Because of non-adiabatic effects, spin and nuclear motion are fundamentally linked. The old model of an electronic state, followed by a separate spin flip step, is an oversimplification. The true physical objects are tangled spin-vibronic states. Defining spin-orbit coupling as the interaction of spin with orbital motion is an incomplete description of its mathematical role. This table summarizes the broader impact. This interaction is a fundamental reorganization of the symmetry structure of the entire Hamiltonian. It splits degeneracies, alters absorption maxima, and provides the pathways for electrons to hop between different multiplicities. When light interacts with matter, it does not see the simplified labels found in introductory textbooks. It interacts with the actual, heavily mixed eigenstates of the physical system.